Hey class, it's me, Mrs. Mack. I'm here to read aloud the notes to you guys and do a little lesson through Screencastify. So today's topic, it is a new topic. It's on geology and plate tectonics. So if you look, you can kind of listen and go through the notes and kind of just have me playing in the background to kind of talk you through it. Or you can kind of just watch with me as I go. So the definition of geology, if you break apart the word based on our prefixes and suffixes, geo means earth, logi means the study of. So together that word or that definition is the study of earth. So we've already been discussing last week the rock cycle. We talked about the geological time scale. So we're going to talk more about our earth. And that's kind of where we're going to begin. Many of you guys have a little bit of background knowledge on understanding about the structure of our Earth. So we have the inner core, the outer core, sometimes just referred to as collectively the core. Then you have the mantle, which is very important. We're going to talk about the convection currents that occur in the mantle that allows for our crust, which is the outside boundary where we live. So that's kind of your breakdown. So we're going to start in the very middle. Think of the Earth as kind of like a gumdrop. Okay, so you have all these different layers, and they each are kind of categorized based on their composition. So the inner core is hot. It's thought as to be as hot as the surface of the sun. We don't know because we can't even think about even getting close to it, right? We do know that it is a solid, and it's composed of the two elements of iron and nickel. If you look at the outer core, again, it's still composed of iron and nickel, but it's a liquid. So it's hot, but it's not as hot as the inner core. So, geographically speaking, or if you look at it structure wise, the deeper you go, the hotter it is. So you have the inner and outer core both made or composed of nickel and iron. And then you have the next part, which is your mantle. The mantle is kind of where the magic happens. The mantle is still hot, but not as hot as the core. It is the largest layer of Earth, and it's composed of a wide variety of materials. So it's both solid and liquid, and it's kind of like I said, right under Earth's crust, which is our last component. The crust is cool. It's what we live on. It's composed of rocks and various materials that make up the crust. My question for you, is it a solid or a liquid? Well, if you look at the next slide, it is a solid. Even though 70% of Earth's surface is water, there is still crust under that water. The water sits on top of the crust. So the whole outside surface of our Earth is a solid. That's what we refer to as Earth's crust. What we're going to be talking about in the next couple slides is kind of how those plates or how our crust moves. So Earth's crust does move. They say it moves a couple centimeters every year, depending on what plate you're existing on. So the continents have not always been arranged like they are today. If you look at this, the Earth's crust is divided into segments called plates. So if you look carefully, these are all different colors. They all have specific names. There's major and minor plates, which we'll talk about coming up, but they're all kind of on Earth's surface. So we are a solid as Earth's crust, but those plates are kind of moving. If we were in class, I'd think of it as like a little sponge floating on in a big bowl of water. Okay, so it is a solid, but it still can move based on the current of that water. I would usually do that demo in class. So in 1910, Alfred Wegener, a German scientist, hypothesized that all of the continents had once been joined together in a single landmass and have since slowly, and I'm talking slow here, drifted apart. He named the supercontinent Pangea, which means all lands. This idea of the continents moving became known as continental drift. If you look at that word root, think of continent. So this is kind of what they hypothesize. You might see this even if you type into Google and type in Pangea. You'll have similar graphics that kind of come up, how all of our continents were once one. They also know this based on the fossil record. So they have found similar fossils across, for example, South America and Africa, or over here into Africa and Antarctica. And that's kind of how they can hypothesize. Um, how they can hypothesize the actual location of where these previously existed. You can see over here, it might be a little hard, but these are the different Jurassic, Triassic, different periods, and they're saying over time. So most scientists originally rejected Wegener's theory because he could not identify a force that could move the continents. And again, this was in the 1910, so over 100 years ago. We now know that today that this movement of the plates is called by something known as convection currents in the mantle of our Earth. So I usually talk to you guys about boiling water. If you've ever heard of with steam of the boiling water, I always say if you're taking a really hot shower and all the doors are shut in your bathroom, and then automatically you open up the door, what's going to happen is the steam is going to kind of move, right? And is there more steam up or is there more steam down? Well, typically what happens is that heat is going to rise and cool air is going to sink, right? So that's kind of why the steam is always up in the bathroom opposed to down low by your feet. The same thing happens with convection currents. So convection currents are caused by a very hot material at the deepest part of the mantle rising. Then they get hot and then they're going to cool, sinking again, and then heating and rising, repeating the cycle over and over again. So that's kind of it's kind of how it works there. The more heat is found from the core, so in that case, it's going to cause that movement pattern of moving those plates, even though very slowly. And I love this visual here. You can see the arrows all underneath of it. You can kind of see how they're cyclical, right? This is all in the mantle. This is your outer core and your inner core. And you can kind of see how they're constantly moving, which is going to cause that crust or your plates to also move. Okay, so that's kind of what your convection currents are happening. So later, about 55 years later, in 1965, a Canadian scientist, J. Tussaud Wilson, okay, Mr. Wilson, observed that there were cracks in the continent similar to those on the ocean floor. He proposed that the lithosphere, which is the fancy word for the crust, was broken into separate sections called plates. Wilson combined what geologists know about seafloor splitting, or Earth's plates and continental drift, into a single theory, which then became known as the theory of plate tectonics. So, plate tectonics is the geological theory that states that pieces of Earth's lithosphere, again, fancy word for the crust, are in constant slow motion, driven by the convection currents in the mantle. Again, the mantle is that middle layer found under our Earth. The theory of plate tectonics explains the formation, movement, and subduction of Earth's plates. There are a total number of 52 tectonic plates in the world today. 14 of them are major, and 38 of them are minor. So the next set of our notes now is going to be talking about plate boundaries. Plate boundaries are really important because we're going to talk about those kind of floating sponges on that water, or thinking about the plates on our Earth, on our planet. They're going to coincide, okay, or kind of come near other plates. So we're going to talk about the interactions that typically occur at those plate boundaries. Okay, so the different pieces of lithosphere meet at the lines called plate boundaries. Faults, which are breaks in Earth's crust where rocks have slipped past each other, form along these boundaries. So these are the three different types of plate boundaries. You have transform boundaries, divergent boundaries, and convergent boundaries. And if you know or have ever seen those words before, you might be able to infer as to what type of plate boundary, kind of how are they moving past one another or with each other. So first is the transform. Transform plate boundaries move along the boundary in the opposite direction. San Andreas Fault, which hopefully you've heard of before, I know there's a big movie out about it, is an example of a transform boundary. The Pacific plate is sliding past the North American plate. So if you look here, here's your example. Say this is the San Andreas Fault line. This is your California. Alaska's up here. But here's your California. So that's a plate boundary. And if you look at these arrows, that's kind of an indication for you. So the arrows are going up and this one is going down. So as they're slipping past each other, there's a lot of pressure that results there, which if you know anything about California, what typically happens in California? You're right. Earthquakes. Earthquakes happen a lot at transform plate boundaries. Next is divergent. So you can kind of see the little visual here. If you divergent, you're thinking different. So they're going in different directions. So when two plates move apart or divide, it's called a divergent boundary. Couple examples: the Mid-Atlantic Ridge, which is actually happening in the Atlantic Ocean, which is right off our coast. So what's going to happen? It's called seafloor spreading. So they're going to go apart from one another, and the magma and the lava that's in your convection currents in the mantle, it's going to kind of come up and fill in that empty spot. You also have things on Earth called rift valleys, and the Rio Grande Rift was an example of that divergent boundary, which I have a picture of right here. So you can kind of see that opening that's actually occurring. So on land, it looks like this. On water, it looks like this. Trenches, a lot of times, students think of them as divergent boundaries. In the Mid-Atlantic Ridge, again, here we are here in New Jersey, right here, and the Mid-Atlantic Ridge kind of goes right across in our ocean. The last one is convergent boundaries. So convergent boundaries is when two plates come together. So C come together. When two plates converge, the result is a collision. So depending on where that's happening, that could happen on land, on water. What I like to explain to you with convergent boundaries is if there's one on land and one on water, whatever one is more dense is actually going to sink below it. So that would kind of happen in this example right here. You can kind of see here, since they're kind of going together, if it's more dense or it's heavier, it's going to go down. And that's going to be how they're formed. Another great example with land to land plates come together, they form mountains, right? So the Appalachian Mountains, which run up and down our East Coast, has formed over millions of years as a result of a convergent boundary. When two continental plates collide. Undersea volcanoes also form when plates collide, which is kind of that middle one. Okay, so there were your three examples. There's a really good video clip here, especially if you're a visual learner. Please log into the Brain Pop there and watch that. It reviews all the different plate boundaries and talk to you a little bit about what we're going to talk about next, which is natural disasters. So things can go a lot of times at these plate boundaries, things happen, right? So earthquakes, volcanoes, tsunamis, which we'll talk about, these are all kind of natural disasters that we've heard of, but do we really know the science behind them? So stresses on Earth's crust produce compression, tension, and shearing in rock. Sometimes faults occur, which are cracks in the Earth's crust from the result of stress, just like I showed you out in California, the San Andreas Fault. Faulting and folding of Earth's crust cause mountains and other features to form on the surface. So an earthquake, which I'm sure you've heard of before, is the shaking and trembling that results from the movement of rock beneath Earth's surface. The movement of Earth's plates creates powerful forces that squeeze or pull on rock in the crust. These forces are examples of stress and a force that acts on rock to change its shape or volume. There is another brain pop that if you want to watch that, they categorize, seismologists categorize them based on the magnitude. So like a 10.0 is like not the highest ever recorded, but that's the largest scale, whereas 0 is nothing. So you kind of can range all throughout that scale every second of every day. You're actually going to be doing an activity later on in the week that discusses that. If you look here, largest earthquakes in U.S. history, believe it or not, a lot of them came, if you look at this list, came in Alaska. And that's because they're right on that plate boundary that I showed you before. And I believe the scale was, if you look there, 9.2. And look at that. I mean, look at that road. Look at the cars, right? So crazy, crazy things happened. And that was in 1984. If I can read it correctly. So that was Prince William Sound. So, and that was in Alaska. And Alaska is part of the United States. So you can see another little graphic there too. So yes, believe it or not, New Jersey has had earthquakes. We're not on a plate boundary, but a lot of times we can actually feel the aftershocks of that. So these are some resources if you want to learn more about earthquakes. Lastly, volcanoes in the United States. When thick magma and large amounts of gas build up under the surface, eruptions can be explosive, expelling lava, rocks, and ash into the air. Less gas and more viscous magma usually means a less dramatic eruption, often causing streams of lava to ooze from the vent. So you think, when you think of a volcano, you think of the magma and the lava based on where it's found, exploding out of the volcano. Realistically, that's how most volcanoes actually act. But you can see here, this is Mount St. Helen. I'm sure you've heard of that before. It actually didn't go up as expected. It kind of went out the side when that erupted. And then lastly is a tsunami. Tsunami is a giant water wave that is formed when the earthquake jolts the ocean floor and causes plates to move. So tsunamis always start over a body of water, and then it's basic, I don't want to say a tidal wave, but you can think of it as that. That kind of comes on shore with a lot of force. This was the tsunami recently off the coast of Asia, or the Asian shoreline. You can see the before and the after and the devastating effects that result from that. So, like I said, I just wanted to spend some time kind of reading over the notes to make it easier for you. Of course, we wish we were with you in class so we can kind of talk you through them. But I thought this would be beneficial for you guys. Thank you for listening. Of course, if you have any questions, please reach out to your teacher. Have a great day.